Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 20th, 2025, about 3 days ago, and this paper proposes a new way to generate three-dimensional textures directly in three-dimensional space instead of stitching together multiple two-dimensional views. It treats texture as a dense three-dimensional color field and shows that a latent diffusion model can produce far more coherent, well-aligned textures than multi-view diffusion pipelines, while still being efficient. The paper is titled NaTex, Seamless Texture Generation as Latent Color Diffusion. And as we will see later, the native three-dimensional approach delivers striking gains in both visual quality and flexibility for texture workflows. Alright, the introduction just laid out the motivation, and Figure 1 makes that promise very concrete. Figure 1 shows a whole scene of stylized three-dimensional assets, all textured from just a single reference image. The textures stay crisp across complex shapes, which means edges, tiny details, and rounded parts all look clean and consistent. The collection also mixes characters, props, and buildings, so it highlights that the method generalizes across very different object types. Well, Figure 2 contrasts multi-view diffusion with the native three-dimensional approach on three core issues. The whole figure shows pairs of examples, with the top row from multi-view diffusion and the bottom row from the native method. The occlusion column highlights ghosting and bad inpainting in hidden corners that disappear when colors are generated directly on the surface. The alignment column shows misregistered edges around windows and pipes that become clean and snapped to geometry. The coherence column illustrates color discontinuities across a truck bed that turn into a smooth, globally consistent material. So, while Figure 2 highlighted the failure modes of multi-view pipelines, Figure 3 lays out how the new system actually works end-to-end. The left panel shows the geometry-aware color VAE, which turns a three-dimensional color point cloud into compact tokens and then decodes them back to a textured mesh. The center panel presents the multi-control color diffusion transformer, which takes image, geometry, or existing texture encodings and generates new color tokens. The right panel demonstrates that this pipeline supports texture generation, part-based recoloring, and full material rendering with realistic lighting. Alright, Figure 4 explains how the diffusion transformer combines multiple control signals to drive texture generation. The left side shows geometry and color encoders that turn a textured mesh into geometry tokens and optional color tokens for color control. The right side shows an image encoder that produces image tokens for image control, so a reference photo can steer the look. All these tokens are merged with noisy texture tokens, then passed through double-stream and single-stream blocks that use positional rotary embeddings to keep everything aligned in three-dimensional space. So while Figure 4 focused on the control signals during generation, Table 1 reports how well the color VAE reconstructs textures at different latent sizes. The table shows that larger latent sets steadily improve all metrics, with peak signal-to-noise ratio rising from about 29 to 31 decibels and structural similarity nudging toward 0.99. At the same time, the perceptual error LPIPS drops, which means reconstructions look closer to the original textures across rendered views. Alright, well, Table 1 quantified reconstruction quality. Figure 7 gives a side-by-side visual comparison against other texture generators. The figure shows 4 example assets, each textured by Material MVP, Rodin Gen 2, Tripo 3.0, and NaTex. Competing methods often blur or misalign details around sharp edges and seams. The NaTex column instead keeps crisp decals, clean borders, and consistent colors that exactly follow the shared geometry. So, after the qualitative side-by-side in Figure 7, Table 2 backs things up with numbers. Table 2 compares several texture generators across 4 metrics: CFID, CMMD, CLIP similarity, and LPI pages S. NaTex achieves the lowest CFID and CMMD, and also the lowest LPIPS, which means the outputs look closest to ground truth. Material MVP edges out a slightly higher CLIP score, but NaTex still delivers the best overall metric profile. So the big takeaway is that treating texture as a three-dimensional color field, with a geometry-aware autoencoder and diffusion transformer, largely fixes occlusions, seams, and misalignment in texture generation. More broadly, it hints that many graphics tasks may move to native three-dimensional diffusion. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.